Earthquakes are the expression of the continuous and slow movement of the Earth's crust, fragmented in several parts known as tectonic plates. Earthquakes correspond to the sudden release of stored energy that radiates seismic waves. At the Earth's surface, earthquakes may manifest themselves by the shaking or by causing rapid movements of the ground, leading to loss of life and destruction of property. Seismic waves are the energy waves caused by the sudden breaking of rock within the Earth. They convey the energy that travels through the Earth, inducing rapid cyclic movements at the base of the buildings hit by the earthquake, meaning that strong inertial forces appear. Seismic hazard is the study of predicted earthquake ground motions at any point on the Earth. There are places in the world where the seismic hazard is higher due to their proximity to the lines of intersection between different plates. Seismic risk analysis takes the results of seismic hazard and evaluates the impact of the earthquake on buildings. Assessing the seismic risk is a key issue in the conservation of cultural heritage buildings in earthquake-prone areas. The complex structure of historical buildings makes it difficult to predict their behaviour during earthquakes. There are many examples of severely damaged or even collapsed monuments of inestimable architectural and cultural value. The 1997 collapse of the vault of the St. Francis Basilica in Assisi, Italy. The tragedy of the 2001 Bhuj earthquake in Gujarat, India, taking its toll on the rich architectural heritage and culture of the region. The destruction of entire cities, such as Lisbon, Portugal, 250 years ago, and Reggio Calabria and Messina, Italy, 1 century ago. In the framework of the EU-India ECCP project, Improving the Seismic Resistance of Cultural Heritage Buildings, aimed at the preservation of ancient masonry structures, with regard to the seismic risk, different investigation and analysis procedures were applied to 4 emblematic historical structures located in Portugal, in Italy, in Spain, and in India. The Qutub Minar is the highest stone tower in India and one of the tallest stone masonry towers in the world. Its construction began during the reign of Qutb Minar around 1202 and was completed by his successor Muhammad bin Sam. The Qutub Minar, rising to a height of 72.5 metres, is composed of an external circular polylobed shell and a cylindrical central core. The core and the external shell are connected by a helical stairway with 379 steps made of Delhi quartzite stone. The Minar outer shell is composed of a 3-leaf masonry wall. In the first 3 stories, the external veneer is made of ashlars of red and buff-coloured sandstone, while the inside is composed of Delhi quartzite ashlars. In the 2 upper stories, the external veneer is made of white marble stones and the internal of red sandstone. The infill is made up of stone masonry rubble. Managed by the Archaeological Survey of India, the Qutub Minar has constantly been the object of restoration and maintenance work since it was built. As with all monuments in the care of the Archaeological Survey of India, there is a regular annual monitoring and maintenance plan, combined with a running programme of special restoration projects. The Qutub Minar Tower and Complex were registered in the UNESCO World Heritage Monument List in 1993, as an outstanding example of the architectural and artistic achievements of early Islamic India. The research programme includes a plan of action based on a multidisciplinary approach, entailing aspects of risk analysis, modern techniques for surveying and monitoring applied to monuments, and advanced computer simulation of reality in a virtual environment. The objective is to provide recommendations for the conservation of historical buildings in seismic regions, based on a thorough understanding of their structure, construction features, and materials. These recommendations which also take modern materials and techniques into consideration, may help to prevent earthquake-induced damage to buildings. The first step of the analysis for the preservation of monuments consists in the execution of a sound investigation campaign to obtain detailed knowledge of the structure and materials. With this perspective, after gathering information on the history and the present-day damage, several non-destructive tests were carried out on the Qutub Minar, intended to define the dynamic behaviour of the tower and to characterise the masonry conditions. Non-destructive investigations consisted of dynamic identification and sonic tests. Every structure possesses particular ways of vibrating, whatever the source of excitation, such as wind, traffic or seismic events, that essentially depend on its geometry, mass, stiffness and restraints. The vibration characteristics of a specific structure are a precious source of information about the physical and mechanical characteristics of the structure. Ambient vibration tests were thus performed to define the dynamic response of the Qutub Minar. Dynamic tests were carried out by using devices called accelerometers. These very sensitive transducers measure accelerations 1 million times lower than the value of gravity, defined as micro-g. They were fixed to the structure in several positions at different heights in order to evaluate the dynamic parameters of the tower and to proceed with the modal identification. As a benchmark, data acquisition systems of 3 different countries have been employed in this task. Modal identification strategies allowed the definition of several natural frequencies and corresponding modes. The comparison with the results obtained by the acquisition systems of the different partners indicated an excellent match between the obtained frequencies. Sonic tests are applied for measuring the transit time of elastic waves in masonry structures. This transit time and the calculated sonic velocity provide information about the quality and consistency of the masonry element under investigation. The velocity is influenced by the composition of the masonry, as well as by the presence of inhomogeneities, voids, and deteriorated areas. Results from sonic tests carried out on a corner at the base of the tower qualitatively defined a masonry with fair compaction characteristics. Finally, a monitoring system designed specifically for the tower was installed, with the aim of characterising the response of the structure to the seismic activity. The system starts to record the data when the signal exceeds a predefined threshold based on local vibration conditions. To properly evaluate the safety of an existing building, it is necessary to adopt suitable modelling strategies and to take into account the characteristics of the selected materials. In fact, masonry presents rather complex mechanical properties. A simple description of the material is not possible, since it does not respect common hypotheses, such as an isotropic, homogeneous and linear elastic behaviour. For this reason, suitable representation of materials must include cracking and crushing of masonry when subjected to the different loads. Different structural models of the Qutub Minar were prepared to assess its seismic safety, using a tool that engineers denote as finite elements analysis. The models are representative of the way forces flow in the structure when subjected to different loads, for example, self-weight and seismic actions. Once calibrated, they can be used to estimate the safety of the structure. The models considered to simulate the structural behaviour of the Qutub Minar take into account the different materials of the structure: the external 3-layered wall with the internal rubble masonry, the stairway, the inner core. Also, doors and openings can be taken into account. The actual weight of the structure was applied to the virtual model. This provided an indication of the present flow of forces inside the tower. Natural frequency analysis was carried out to validate the model using the data obtained in the experiments. A good comparison was obtained, since the experimental mode shapes are very similar to the ones defined by the numerical models. To evaluate the dynamic behaviour of the Qutub Minar, and therefore assess its safety with respect to earthquakes, dynamic and equivalent static analyses, assuming cracking and crushing of masonry, were selected. These are sophisticated analysis tools not yet widely available in engineering practice. With the pushover analysis, a set of horizontal forces, or accelerations, is applied to the structural model to simulate the seismic action. It is then possible to draw a capacity curve representing the displacement of a control point of the structure versus the load set applied. Another, more precise approach uses a non-linear dynamic analysis, since a real seismic event is simulated through the application of a synthetic accelerogram, or an accelerogram recorded during an earthquake at the base of the building. Then, the structural response of the building can be evaluated. Several accelerograms, compatible with the response spectrum defined in the Indian Seismic Code, were applied to different models of the Qutub Minar. The dynamic analysis proved to be more representative with respect to the seismic behaviour of the Qutub Minar, since it can detect a number of peculiar vibrational characteristics of the tower that cannot be appreciated by applying a conventional pushover analysis. The earthquake load simulations indicated that the structure generally manifests moderate displacements up to the third balcony, and a localized large amplification, in terms of accelerations and displacements, is detected in the upper part of the tower. The research work carried out within the project represents a valuable effort to understand the structural behaviour of masterpieces of European and Indian architecture and culture. The knowledge of the structures proved to be crucial in the definition of advanced structural models used for the assessment of the selected buildings. It is therefore essential to acquire an in-depth understanding of cultural heritage buildings. As these buildings represent the genius of our predecessors and the identity of our cultures, we should strive to keep them in perfect condition for the generations to come.